Chapter 25, Statistical Thermodynamics, Section 25.8, Helmholtz energy and Gibbs energy. The average energy of the particles in the NVT ensemble can be calculated using these equations. The average energy is equal to negative dlnq over d beta, or kBt squared dlnq over dt, or kBt dlnq over dlnt. The internal energy of the system relative to the 0K internal energy is this. It's N, the number of particles, times the average energy over here. So it's N times kBt squared dlnq over dt. And because N times kB is nR, so we have this expression as well. And also, we can write U relative to 0K internal energy is nRT times dlnq over dlnt. This comes from this expression times the number of particles. So now we can write this equation. The internal energy of a system minus its 0K internal energy is equal to nRT times dlnq over dlnt. So this is the so-called thermal correction to the internal energy. This is always positive. U at 0K is the sum of the ground electronic energy, which includes the nucleus repulsion, and also the 0 point vibrational energy. We have also derived this expression for entropy. Entropy is equal to nR times dlnq over dlnt plus lnq. Given U, given S, we can get the expression of the Helmholtz energy of the system. So A minus the internal energy at 0K is U minus Ts minus the 0K internal energy. And we have this, which is nRT times dlnq over dlnt right here, and minus Ts. Ts is equal to nRT times the sum of these two terms. One is dlnq over dlnt, the other is lnq. So we have 1, 2, 3 terms, but the first and second terms cancel. So the result is really simple. The Helmholtz energy of a system minus the 0K internal energy is negative nRT lnq. And we have this equation here. Now look at this equation and this equation. They are pretty simple. U minus 0K internal energy is nRT times dlnq over dlnt. A minus 0K internal energy is negative nRT lnq. Helmholtz energy can be expressed in terms of the partition functions. A minus 0K internal energy is simply negative nRT lnq, and because Q is the product of translational, rotational, vibrational, and electronic partition functions, we can express lnq in terms of the sum of these 4 components. Now, because dA is negative SdT minus PdV from thermodynamics, we know pressure is negative delta A over delta V under constant temperature. And then this is equal to nRT, come from here, times, well, the first derivative of the sum of lnq trans, lnq rod, lnq vibration, lnq electronic on top with respect to volume under constant temperature condition. And this equation for pressure can be used to derive the ideal gas law. Now let's look at ideal gases. For ideal gas, we can get the expression for the translational, rotational, vibrational, and electronic partition functions. The last 3 components do not depend on volume at all. So if you take the derivative of Q rod over delta V, it's 0. the derivative of Ln vibrational partition function over delta V is 0, and the derivative of the logarithm of electronic partition function with respect to volume also 0, and therefore we only have the first term left. Now pressure is just nRT times the first derivative of the logarithm of the translational partition function. And for ideal gas, we know its translational partition function. It's 2 pi m kBt to the power of 1.5 times volume over the Planck constant cubed. And this logarithm can be separated into the logarithm of V plus the logarithm of everything else. Everything else does not depend on V, and therefore we have only the first derivative of the logarithm of V, which is 1 over V. So this whole thing is just 1 over V, and therefore P is nRT over V. PV equals nRT. We can also derive the expressions for enthalpy and Gibbs energy accordingly. So enthalpy minus the 0K internal energy is U plus PV minus 0K internal energy. And U minus U of 0K is nRT times dlnq over dlnt. And then plus PV, that's enthalpy. Gibbs energy minus the 0K internal energy. Well, because Gibbs energy is A plus PV, we have this expression, and we know A minus 0K internal energy is negative nRT lnq, then G minus the internal energy at 0K is simply negative nRT lnq plus PV. The 0K internal energy is the sum of the ground electronic energy and the 0 point vibration energy. In this ground electronic energy, the nucleus electrostatic repulsion is included. At 0K, know this: U equals H equals A equals G at 0K. Just because at 0K PV is 0, TS is also 0. Using the 0K internal energy as the 0 reference, we have these expressions, 5 of them. We have entropy, which is nR times the sum of two terms, dlnq over dlnt, and lnq, the sum of these two terms. We also have U minus 0K internal energy is nRT times dlnq over dlnt. Helmholtz energy minus 0K internal energy is negative nRT times lnq. Enthalpy minus 0K internal energy is nRT times dlnq over dlnt plus PV. Yeah, just because H and U differ by PV. G minus 0K internal energy is negative nRT lnq plus PV, just because G and A differ by PV. For monatomic ideal gases, we have a really simple expression for Q. Q is simply the translational partition function times the electronic partition function. The translational partition function is 2 pi m kBt to the power of 1.5 times the volume over Planck constant cubed. The electronic partition function is G sub 0, assuming we can ignore the excited states. For linear molecules that behave ideally in the gas phase, given the rigid rotor approximation and the harmonic oscillator approximation, Q is Q trans times Q of rotation times Q of vibration times Q of electronic. And then we have the translational partition function here, 2 pi m kBt to the power of 1.5 times volume over Planck constant cubed. The rotational partition function is kBt over sigma hcb. Sigma is the symmetry factor. B is the rotational constant. H times C times B equals h bar squared over 2I, where I is the moment of inertia. And now we have the vibrational partition function. We have 3 n minus 5 vibrational modes. For each vibrational mode, this is the partition function, 1 over 1 minus e to the power of negative h nu sub I beta. Nu sub I is the frequency of the ith vibrational mode. Beta is 1 over kBt. Finally, the electronic partition function is assumed to be just G sub 0. For nonlinear ideal gas molecules, the expression of Q is as follows. We have the same translational partition function, but the rotational partition function looks different. It's the square root of pi over sigma, and then square root of kBt over hcB1, square root of kBt over hcB2, square root of kBt over hcB3. B1, B2, B3 are the rotational constants. And then the product of all those vibrational modes, 1 over 1 minus e to the power of h nu sub I beta. Nu sub I is the vibrational frequency of the ith vibrational mode, and the beta is kBt. Finally, G0 is the electronic partition function. It's G0 assuming the first excited state minus the ground excited state. The difference is much greater than kBt, so we can ignore the excited states. So this is how we get Q for atoms, for linear molecules, and for nonlinear molecules. Once we have the expression of Q, we just plug in Q here, 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 and here. We will be able to get the expressions for entropy, internal energy, Helmholtz energy, enthalpy, and Gibbs energy. Now get back to the wheel of thermodynamics. A is U is A plus Ts, A is H minus PV, H is U plus PV, H is G plus Ts, G is H minus Ts, G is A plus PV, A is G minus PV, A is U minus Ts. And also we can have expressions of U, H, A, and G relative to the 0K internal energy. For U, it's nRT times d ln(q) over d ln(t). For A, it's negative nRT ln(q) relative to 0K internal energy. H is simply PV plus U, and G is simply A plus PV. So we have this wheel of thermodynamics. And again, to determine those thermodynamic functions, all we need is the expression of Q, the partition function of the system. And Q is equal to the product of translational partition function, rotational partition function, vibrational partition function, and electronic partition function.